Let more people join and then we will start. I can only see 27 people here. Okay, so good afternoon, everyone.
Good afternoon, sir.
So in the last lecture, we were studying this minimum mode configuration for 8086, and we said there that minimum mode configuration is the mode in which your processor 8086 is the only processor in the system. Rest all devices which are connected to it, they can be the peripherals, like they will not be individual processors in themselves, right? And in the last lecture only, we have paid attention to this 8284 clock generator chip because as we discussed that in 8086 or 8088, there is no input for crystal oscillator. There is only a single input for the clock. If you see the pin diagram, there is a single input for the clock. Okay, let me record the lecture also. Yeah. So for this 8086 case, we discussed that there was only single clock input pin, and at that input you have to supply the clock waveform. So on that note, since there are no two input pins for the crystal oscillator, we had to had this IC 8284 clock generator, right? And this IC is a multifunctional IC, which apart from generating the clock for 8086, will perform many other operations like ready and reset signals could be generated. And this peripheral clock, which is 6 times slower as compared to what has been applied at X1, X2 or EFI, whichever is selected, is made as output here. And that will be decided by this F/C, that is whether you are selecting the crystal oscillator or you are selecting the external frequency that you have applied here, that is selected. So if it is 0, if this F/C signal is 0, that means you are operating with this crystal oscillator, right? Then these signals need to be grounded for the minimum mode of operation. And this clock generator was also taking ready 1 and ready 2 from the other peripherals that are interfaced to the complete microcomputer system, right? We also saw the typical minimum mode configuration in that you had this 8086 microprocessor, and together with that, this clock generator is attached. And here you saw there are two different set of ICs. First IC is for latching the addresses, and the second IC is an optional set of IC which is used for keeping the data from the data bus or keeping the data from the external world such that the data can be transferred. So this is called as trans receiver IC, right? And then you had these control buses. Now this was the important part because the control signals that are generated for this 8086, they will be comprising of memory slash input output, write, read, hold acknowledgement, interrupt, and then interrupt bar, right? So in the pin diagram, if you see, there are separate pins for minimum mode. I mean, the set of pins can be interpreted in different ways for minimum mode and maximum mode. So those minimum mode pins, they had this meaning for this context. So these were used in the control buses, right? We also saw the internal structure of 8284 clock generator, where we saw that how this crystal oscillator frequency X1, X2 or the external frequency is selected by these set of logic gates and how this I mean, if you apply any frequency here, the 1 by 6th of that frequency will appear at the clock PCLK output, which is peripheral clock. So how that all thing is done. Then we saw the meaning of these signals. They need to be grounded for minimum mode of operation. And this was the internal structure of clock generator, although not important from programming perspective, but from here you might get an idea that because of the construction of this 8284 clock generator, some signals might be edge triggered or some signals might be level triggered, right? So that's what we got an idea of. And then we moved on to the complete microcomputer system, which is comprised of the processor, and then you will have a clock generator IC, then you have latches, which we have already seen, and then there are these set of memories, right? So these set of memories, as you can see, they are divided into odd and even banks, and we saw a detailed description of what odd and even bank mean and why we have odd and even bank in existence. The existence of odd and even bank is just because 8086 is a 16-bit processor, and in one machine cycle, if you want to write or read the data of complete 2 bytes from the externally interfaced memory, you cannot do it by a single memory chip of 1 megabyte. You have to divide the chip into 2 parts. You have to actually physically take 2 different chips of half megabyte in size, and you have to connect them as odd and even parts, and that way you will be able to write a complete word into the externally interfaced memory in one machine cycle, or you will be able to read that, right? And for the purposes of writing the operating system, we had this EPROM or ROM, and for the purposes of providing the memory to user, we had RAM, where the usual programs will be written, right? And we can also interface some input output devices. They have been connected to the system through this BHE bar and A0 signal, and of course the address and data bus are connected to every piece of memory, and A0 and BHE bar, they played an important role in deciding whether 1 byte is to be written in one machine cycle or 2 bytes are to be written in one machine cycle. So we had a detailed description of this, right? And after that, we also saw this decoder logic. So by using this decoder logic, several signals in this selection of the memory will be activated or deactivated, right? So this was the typical minimum mode configuration that we saw. And now in today's lecture, we are first going to discuss the timing diagrams for the minimum mode, and then we will see the maximum mode operation, which will be similar to the minimum mode operation. There will be not much difference. The only difference will be in the way the control signals are generated. What do I mean by control signals? These are the control signals, because in the actual pin diagram, if you see, there is a set of pins which can be interpreted as something in minimum mode, and it could be interpreted as something else in the maximum mode. So we all, I mean, minimum and maximum mode operations, they will be similar from the perspective of hardware. The only point of difference will be there in this control bus. So that is what we will be seeing for the maximum mode today. But before that, let us see a general introduction to the timing diagrams of minimum mode, right? So for that, let us first note some few points. We will develop some theoretical few points before that, which will help us understand these timing diagrams better. Although we have studied timing diagrams for 8085 already, so on the similar lines, here the operations will happen, right? So for a typical instruction in 8086, at least 4 timing cycles will be consumed. 4 T states will be consumed. T1, Yeah, so sorry, there was this internet glitch, but no issues. We will continue from where we left. So we are now going to. Am I audible to everyone?
Yes, sir.
Okay. So we are now going to study first of all the typical 4T states, although more or less can be consumed for a particular instruction, which we will see in the laboratory sessions. But typically 4T states will be consumed for most of the instructions. So we will discuss them first one by one, and then we will see the corresponding timing diagram. Right. So in T1 state, you all can guess that an instruction could typically access the externally interfaced memory, or it could not access the externally interfaced memory, right? So in typical T1 state, if we want to access the externally interfaced memory either for reading or writing, the first operation that will happen is the address latch will be enabled. The address latch will be enabled because if you see the actual diagram, if you see the actual system diagram, in that, in the first part of instruction, if you want to access this externally interfaced memory, the address of this externally interfaced memory has to be available somewhere, and microprocessor, through the instruction that it has received, it will be putting the address onto the address latches. There are three latches that you see here, three set of ICs that you see here onto
So,
which the address is. Yeah, tell me.
so the screen is not shared.
Oh, sorry. Yeah. So is the screen visible now?
Yes, sir.
Yeah. So now, if you we are discussing this T1 state first. So in the T1 state, what will happen is addresses will be latched first, and 8282 latches the addresses. So if you see the actual hardware diagram here, the 8086 microprocessor will decode an instruction, and if it has to deal with the externally interfaced memory, which is placed here, as you can all see, then the address has to be first of all given. So address will be given on the address bus that will start from this AD0 to AD19, and it will be latched into these things. So for that, this ALE signal has to be activated. So in the T1 cycle of a typical instruction, the addresses will be latched onto the address latch. That's what will happen in this T1 state. Now in T2 states, the address signal are lowered. That means the ALE signal, it will be lowered, and so the status signals are active. I mean, when the address signal is lowered, when the ALE signal is lowered, then the status signal will become active. The control bus signals that we had, they will become active. And what signals will become active? DEN bar is lowered to enable the trans receiver. So let us see the physical diagram. So if you see, once the address has been stored in this particular set of latches, three latches, so we know which memory location to access. Now after that, our purpose is uh, to enable this trans receiver IC, because we are going to perform either a write operation or a read operation. So for that, we will be needing this trans receiver IC, and if you want to activate that, you have to enable this DEN signal, DEN bar signal. So since this is an active low signal, it will be activated when we will supply it with a value of 0. So that is why this DEN bar signal has to be activated, and this trans receiver IC will become active, right? So this DEN bar signal will be lowered in the typical second T state. What else will happen with that? This read slash write bar signal is activated. I mean, if you want to read, you have to activate the read signal. If you want to write, you have to activate the write signal. So if you see here, you have got this data transmit slash receive signal. This signal will be changed accordingly. I mean, whether you want to transmit the data or receive the data from this trans receiver, so this thing has to be done. And if you correspondingly see here, you have got this read bar and write bar signal. Sorry, not this data slash transmit slash receive signal. This read and write bar signal is here. This signal will be activated, either read or write bar, because we know the address of. Hence, this AD0 to AD15 will go through a high impedance state. Once the data has been transferred from the data bus onto this trans receiver, once the data has been read or written from these externally interfaced set of memories, now the next task is to put that data onto the trans receiver, right? So, here in the T3 state, the data transfer will happen. The actual data transfer will happen, and there will be insertion of additional wait states if it is required. So in T1 and T2 states, in T1 states, mostly addresses were dealt with. The addresses for external memory were dealt with. In the T2 state, you have activated the read or write signals so that the appropriate data can be read or written. And in T3 state, the data transfer will actually happen, right? The data transfer will actually happen, and there will be some additional wait states which are called as TW states. They will be inserted if it is required. If the data is to be transferred is huge, or if the data that you want to transfer is from a slower peripheral, then you have to introduce some additional wait states. So we will see that in the timing diagram. So this is what will happen in the T3 state of the typical timing cycle, right? And then in the T4 state, these read and write bar signals are raised high. That means these are deactivated. We had activated them in T2 state. So in T4 state, they will be deactivated. DEN bar will also be raised high because we want to deactivate that. And this memory / input output signal is set for the next T1 cycle. So these are the typical T states that will be present in most of the instructions of 8086. So now let us see the timing diagram for a typical read or write cycle. So let us see for a read cycle. So these are the 4 T states, T1, T2, T3, and T4. And you will be able to see the clock signal. So in this, as I already told you, the clock will have beginning from the falling edge. Here you had a 1 value, logic 1 value, and here you have a logic 0 value. So from that falling edge, you will assume the beginning of a particular clock cycle, and the next falling edge will be treated as the ending of that T1 state. So this is what we have also seen in the case of 8085, that clocks are designed in such a way that you have to mark their beginning from the falling edge. And this is how 4 T states are shown. Now clock signal is available, and let us talk about T1 state. So in T1 state, mostly we will be dealing with addresses. So when we deal with addresses in the T1 state, ALE signal has to be made high. So you can see that this ALE signal, it has been made high. It is low until T1, and in T1 it has been made high. So because of this printing mistake, this line is not printed here, but it is a connected line. So this ALE signal will be raised high in T1 state. When the ALE signal is raised high, you will see that this address bus, that is AD0 to AD15, and this remaining bits, that is A16 to A19, they will now contain the addresses, right? They will now contain the addresses. So this is the address out, and this is also address out, and these addresses, they will be written onto that IC, which is meant for keeping the addresses. The 3 set of ICs, they will be latching these addresses in the first T1 state. So only these signals are important: address bus and this ALE signal. Rest all signals that you see here, memory / input output bar, and these read bar, data transmit / receive, and this DEN bar, so they do not have any meaning. Whatever their values were, they were kept as it is. But in T1 cycle, these operations will happen, right? And after that, in T2 cycle, mostly we will be dealing with the read and write signals to be activated or not. So in that case, you can see that here you have got this read signal, which was made as 0. That signal is activated because this is a active low signal. So here in the T2 state, that has been activated because this is the input read operation. So that signal has been activated, and you can see that this DEN is also lowered because you want to activate the trans receiver IC. So this DEN is also lowered in this state. And if you see the data bus, this data bus is actually tri-stated. It does not have either data or address, and that stage is called as tri-stated. So this data bus has got nothing to do in this stage because the actual data transfer will appear in T3 state. In first T1 state, you will have address, you will deal with addresses. In the second T state, you will be dealing with activation of reading and write signals, and the transceiver IC will be activated. In the third T state, you will be actually transferring the data. So you can see that in the third T state, this AD0 to AD15, I mean this data bus that you have, which is of 16-bit, it will be flooded with data, it will be filled with data, and you can see here the read signal is still lower. So this data bus, it will contain the data from the external memory, and it will be loaded into this data bus. I mean, this data will be available here, and it will be given to the transceiver IC, and accordingly your microprocessor will read that data. Now, talking about these status signals, you have got some status signals also here, like BHE bar signal is there, and this S3 signal is there. So these statuses will be set, I mean status out will be set accordingly so as to enable this read operation, right? We already know how BHE bar works and how this S3 and these bits work. So they will have appropriate values. It will be set from T2 only, and it will last till T4. So this will be set accordingly, right? In the T4 cycle, all of the deactivation process will begin, right? So the data bus will be emptied. It does not have now any data or address, and this address latch enable signal has also got no meaning, because in the T1 cycle of the next instruction, the addresses are to be latched. So we are just preparing it for going high, and then these signals will also change their status. Memory slash input output bar read signal will be it will be deactivated, and so on and so forth. So this T4 is actually a typical deactivation cycle and preparation for the next instruction, right? So T1 for addresses, T2 for enabling the read write, T3 for transferring the data, and T4 for actually disabling all the signals and preparing for the next T states or next instruction. So this is how a typical input output read operation looks like. And if you see the corresponding write operation, the only change will be there in the right pin. So by mistake, we have written read here in your book also that I have given to you. So this should have been write signal. Instead of read signal, it should have been write signal. So you can make this correction in your books. So I guess a typical timing diagram is now clear to all of you. Is this timing diagram clear to all of you?
Yes, sir.
Okay, so this is a simple enough timing diagram. And in your examinations, mostly in electronics and communication, we ask them to elaborate on these timing diagrams. But from the computer science and IT perspective, you should just know these timing diagrams. And most of the focus we will be having on interfacing and programming portions. But you should know this. I mean, there could be simple questions in your examination like this timing diagram is given. Identify what is going on inside the microprocessor. So this name will not be given to you that this is a write operation. So you should be able to see whether it is a read or write operation. So you should be able to see that in T1 state, the addresses are getting latched. So what is going on inside the microprocessor, it can be told by its timing diagram only. So you should be able to at least read a timing diagram properly, right? Now, after this, let us now come to the maximum mode of operation. This was the minimum mode of operation. Now, today's topic is maximum mode of operation. So, maximum mode of operation is again similar to the minimum mode of operation. This is the minimum mode of operation which we have already seen. And in this maximum mode of operation, you have this kind of computer configuration. So now today we are going to discuss individual components one by one. What are the points of differences between maximum and minimum mode, etc. So that's what we are going to see. Okay. So let me first show you the diagram for pin, because that will be useful. So pin diagram we had studied in the 6th lecture, and let me show you a typical pin diagram. Or not in this way. Let us see this one. Sorry, this is 8085, 8086 pin diagram we need to see. 8086 architecture, 8086 pin diagram. So here we will be able to see the pin diagram. Let's start Yeah. So this is the typical pin diagram of 8086 CPU, and here you can note that there are pins for minimum mode and there is pin for maximum mode. Now, could you notice any ALE pin in the maximum mode of operation? Do you notice that ALE pin is there in the maximum mode of operation? Do you all notice any ALE pin in the maximum mode of operation? Here we have got these minimum mode operation pins, and it has one ALE here, right? And from this pin to this pin again, it will be interpreted as these signals in the maximum mode. So in maximum mode, this ALE pin is missing because ALE pin that you see here, it was available in minimum mode, but in the maximum mode, that pin was missing. So is it that in maximum mode the processor will not deal with the externally interfaced memory because ALE signal is missing? So how will we deal with this externally interfaced memory in maximum mode? Any ideas? Because to be able to provide addresses to the external world, you have to have this ALE signal and these read-write bar signals and I mean this memory input-output signals. So they are absent in this maximum mode of operation. So if they are not present, our purpose is to be able to generate all those signals by using a combination of these signals. So for that, we will require a separate IC because ultimately ALE signal has to be there. If ALE is not there, then the addresses will not be latched into the external latches and you won't be able to access the externally interfaced memory. So here the pins that you see, these are for request and grant 0 and 1, and then you have lock pin, which will lock the internal data and address buses from the external usage. Then S1, S2 and S0, these are the status pins. These are the status pins. Let us see what they mean. So here we have got this S1, S2 and S0. So here you can see that depending upon the bits that they have, the combination of bits that they have on S1, S2 and S0, you will have different meanings. Interrupt acknowledge, read input port, write input port, halt, instruction fetch, read memory, write memory and passing interactive, right? So from these S1, S2 and S0 and a combination of other signals in the maximum mode, we should be able to generate these read-write signals, etc. We should be able to generate these read-write, memory input-output signals, etc. because one of the combinations on S0, S1 and S2 will mean any one of these things, any one of these 8 things. So just by having 3 pins in maximum mode, you are meaning 8 different things, right? So that has been done because in maximum mode, a lot of other processors will be combined. So instead of increasing the number of pins on this 8086 CPU, we brought these status pins S0, S1 and S2, and they will mean these in their context. Similarly, this QS0 and QS1 will tell you the status of queue, and this is what we have already studied earlier. So if you see the status of this queue, for 00, there is no operation in the queue. For 01, the first byte is taken. For 10, the queue is empty, and for 11, the subsequent byte will be taken. Right. So this is some information that we need to keep in mind. And with this in mind, now let us have a look at this diagram of maximum mode of operation of 8086. So in maximum mode of operation, the clock generator 8284 will be interfaced in the same way. It will be interfaced in the same way, right? So there is no change as far as this clock generator is concerned. Now, the pin that will be changed is this minimum/maximum pin. It will be grounded because when you ground it, this IC will operate in the maximum mode of operation. In the minimum mode of operation, we had applied a VCC supply at minimum and maximum pin. However, in the maximum mode of operation, we will simply apply a ground pin so that the IC knows that this time it has to operate in maximum mode of operation, right? Then now, from these status signals S0, S1 and S2, they are supplied to a separate IC which is called as 8288 bus controller. So this is a bus controller. What is the purpose of using this bus controller? The purpose that I have just illustrated in the explanation prior to this slide. The purpose is with these S0, S1 and S2 signals, you will be able to generate memory read, memory write, advanced memory write, advanced input output write, input, output, read and write, interrupt, acknowledge, etc. together with this DEN, DT/Q and ALE signals, because these three pins, DEN, DT/Q bar and ALE, these were absent in the maximum mode of operation for 8086 processor. So they have to be generated separately. So for that you have this 8288 bus controller which is present here, right? So if you want to operate 8086 in maximum mode, this cannot operate independently. It has to take the help of this 8288 bus controller IC, which will be able to generate this address latch enable DT/Q and this DEN bar signal, right? Otherwise you won't be able to access the externally interface memory, because this ALE signal, DT/Q signal and DEN signal, they are connected to these set of latches which will latch the address and the trans receiver. So the trans receiver here is more or less compulsory, because in maximum mode system, keeping a trans receiver is good, because you cannot correct your data lines directly to everything or address lines directly to everything in the system. So trans receiver will be doing that job. So you can see that these signals, they are used as activation signals for these two ICs, and they are not directly available from this microprocessor. However, an interpretation of this S0, S1 and S2 will tell you in some sense when ALE is to be generated. So this is one point of difference. 8288 bus controller IC is there, which is to be used for the purposes of generation of these signals, right? So rest everything, it remains the same. 8288 latch, there will be 3 sets for addresses and trans receiver will be there. Now the internal diagram of 8288 bus controller. So you see here, this is the 8288 bus controller IC, and the internal structure of that IC looks something like this, although it is not very important for us, but just as a piece of information we can keep it. So here you have these latches and trans receiver, which is external to this diagram of 8288 bus controller, and this is the 8086 microprocessor, and this is the clock. So these set of things, they are not a part of this 8288 bus controller IC. The things that you see in this particular region, they belong to the 8288 IC's internal details. And here you can see that as an input you are taking these signals S0, S1 and S2 from the microprocessor, and there will be a decoder. There will be a status decoder. Why we have a status decoder? Because we have seen in this slide that S0, S1 and S2, they can mean 8 different things depending upon the values that they contain. So that is why we need to have a status decoder here. This status decoder will tell the system that what is the interpretation of this S0, S1 and S2 bits. And then this status decoder is connected to control logic, command signal generator and control signal generator. So these are separate sub-integrated circuits. We are not going into the details of how they are made and what they do, but as you can see from their outputs, this command signal generator will generate the control bus, that is memory read, memory write, input output read, input output write and interrupt. So this command signal generator will be generating this control bus signals. Then the control signal generator will be generating ALE, DEN and DD/R, and we will see that this MCE/PDEN is used for peripherals, so that is also there. And this control logic will be generating, it will be taking the input as clock and your VCC, etc. and this AEN and IOB. Now AEN and IOB in maximum mode of operation, they cannot be grounded. Here they have shown it as grounded, but if you ground them, you won't be able to use this 8086 processor with the other microprocessors in the system. So you cannot ground them, you have to use a one value here. So this in this configuration, if you keep it, you won't be able to use this 8086 with the other processors. For using it with other processors, these signals have to be supplied with a high value. So this is not what we desire. It should have been plus 5 volt or a logic 1 value should be supplied here. So this is some internal detail of the 8288 bus controller, just to give you an idea of how ICs are functioning internally. So this is a block diagram which is less relevant to a programmer, but this is how things work there, right? Then now this is a complete system. This is a complete system of 8086 in maximum mode of operation. So can somebody just see this and explain to me what is happening in this system, because this is extremely similar to the minimum mode of operation. So can somebody see it and tell me what is happening here? Any one of you? Raise your hands if you will be able to partially explain it. Okay, how many of you are still present? Please raise your hands. Twenty, 27, 30. 40 people. Okay, so I will ask small questions and you all can answer, right? So this is a typical maximum mode configuration. And what is the point of difference that you see from 8086 in minimum mode in this complete diagram? Please highlight those point of differences. What is the dissimilarity in those two diagrams? Can somebody tell? Is this clock generator applied in the same way? Let's have a look at this clock generator. Is it applied in the same way? Yes or no? Is there any difference in this application of clock generator to 8086 as compared to the minimum mode of operation?
No, sir.
Okay, so is there any difference in context of this bus controller IC? Was this bus controller IC there in 8086 minimum mode? See, if you won't answer, I will put an assignment. I should know whether you know these things or not, or you are just logging in into your system and sleeping. So was this bus controller IC present in 8086 minimum mode?
No, sir.
No, sir.
Okay. Okay. And are these signals that you see, these control signals, do they look different from the control signals that we had in 8086 minimum mode? Yes or no? The control signals that you see here.
Yes, sir.
They are different because in 8086 minimum mode, you can directly obtain it from the processor. But in 8086 maximum mode, they have to be generated through this bus controller IC. So these are the points of differences, and rest everything remains the same. The connection of these memory elements, EPROM and RAM and input output data, etc., they remain the same. And this is, however, not the full mode of operation of 8086 in maximum mode, because you do not see any other processor here. So typically, many other 8086 or arithmetic coprocessor like 8087 can be connected, and you have to use these controls. These control lines can be used here, and other processors can be connected to the system, right? So this is a typical configuration of the maximum mode, and I think it is already self-explanatory, so I'm not elaborating on every component again and again, because the only point of difference was this bus controller IC, right? So now let us see the timing diagrams of this maximum mode of operation. So let me give you a few points about the timing diagram of maximum mode of operation. Yeah. So in maximum mode of operation, again we are going to look at those four stages: T1, T2, T3, and T4, and they will be performing the exactly same thing that they were doing in the minimum mode of operation. The only point of difference will be since here I have written in the T1 cycle that ALE is enabled. Now you should understand that this ALE is different from the ALE of the minimum mode, because ALE signal is not available in the maximum mode. So this has to come from the bus controller. So even if I write here ALE is enabled, so there is a difference between which ALE is enabled. the ALE of the microprocessor is absent in maximum mode. So this ALE that we are talking about is the ALE that comes from the bus controller stage, right? Similarly, this DT slash R signal, it is applied to the IC, and 8288 latches the address. So this 8288 will be latching the address. So typically this T1 state is again going to operate with the addresses only. So here the addresses are taken, but the signals that we are dealing with, they will come from the bus controller IC, right? In the T2 state, we will be trying to transfer the data. So this DEN bar will be lowered, which implies that your trans receiver IC will be activated, and this will enable the memory read control and input output read control activated until T4, right? Or alternatively, you can write also. So you can activate the advanced memory write control or advanced input output write control. So what is the difference between the memory read control and advanced memory read control? The thing is, when we use the word advanced, we are trying to deal with a slower peripheral, right? And what is the difference between a regular memory read operation and an advanced memory read operation? The difference is this: when a slower peripheral is interfaced, it will require some more T states apart from these 4 T states that we are talking here, right? So you have to insert special wait T states until the data is completely transferred. So that is why this advanced mode is there for dealing with the slower peripherals, right? In the T3 state, the actual data transfer will happen. So additional wait states will be inserted in this stage, and then memory write and memory read signals will be activated until T4, and status bits remain active until T3. So T3 is typically a data transfer stage, and T4 is the stage of deactivation of the signals, right? So the same strategies follow. The only point of difference is the signals, they are generated from a different IC this time, right? So if you look at the typical diagram of read operation in maximum mode of 8086, it will also look the same. You will have a clock signal, and you will have these status signals from S0 to S2. So they have also shown the status signals, although it was not necessary, because out of those status signals, we have already found out these ALE signal, MRDC signals, IURC signals, etc. from that bus controller IC. So showing this was irrelevant, but just for the sake of completeness, they were showing these statuses, right? So you can see that in the T1 stage, ALE has to be activated. So this ALE will be activated in your T1 stage, and accordingly the addresses will be latched. So you can see that these addresses are also there. Similarly, in the T2 stage, read and write signals will be activated. So you can see that this signal is activated here. And in the T3 stage, if you see, there will be the data transfer operation. So data transfer will happen here, and you can notice that here is the data bus, and in the T4 stage, the deactivation will take place, right? So this is the maximum mode of operation of 8086, and I believe that these timing markers, they are separated by some amount, because they should be beginning from this particular position. Instead of beginning this from this central position, this should begin from this typical here position, and then accordingly T4 will end here, right? So you can make that shift accordingly by yourself. So this is how the maximum mode of operation in 8086 works, right? So any doubts in this so far? Because there is nothing special about this. This is just a theoretical content. So if you have any theoretical doubts, you all may ask. Okay, so from my side, the theoretical portion of 8086 is complete, because we have seen the maximum and minimum modes also, and your bifurcation of memory into your this even and odd parts is also now known to you. So as per the syllabus, we have completed a lot of things. We began with this 8086 microprocessor architecture. We have completed the pin diagram. We have completed the programming model. And then we went to write some simple programs where we just were introduced to the basic commands of 8086 in 2 lectures, and then we wrote the programs for interrupt. Then we saw the maximum and minimum modes in today's lectures, and we also saw the odd and even bifurcation of the memory. So in the next lecture, which will be the last lecture for 8086, we will be actually reading the addressing modes and some instruction sets of 8086, and that will complete the theoretical description of 8086 microprocessor. And after that, we will be beginning with interfacing of the components. So this interfacing of the components, I could have completed it with 8085 also, but 8086, as I told you, it's a processor which is a blueprint to most of its successors. So that is why we will be trying to interface various components like keyboard, mouse, and various things like DMA, or you will be having programmable peripheral interface, as you can see it here. So various things are there which will be assembled with 8086 to create a complete microcomputer system. So that's what we will be doing from the session after the next session. The next session will be the last session where we will completely cover the addressing modes and instruction set of 8086, right? So if you do not have any doubts, I would like to close this lecture here today. So we are closing a little early, but that's okay because the portion that I intended to cover is covered here. So any doubts, anyone, in this theoretical portion? Okay, so I'll just take the attendance and close this session here.